Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc over in the Helsinki Institute of Physics in the University of Helsinki in Finland, and I'm a cosmologist. So that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I really like being a scientist, and I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want. You can ask me about physics, about science, about space, about cosmology, about academia, about Finland, about myself. You can ask for my hot take on daylight saving time if you want, although you've all heard it before. This is indeed an ask me anything. You can ask me anything you want, and I will do my best to try to answer. If you're a regular, welcome back. Great to see you here. If you're a first-time viewer, welcome. Also great to have you here. No matter how long you've been here, first-time regular, please do feel free to like the video, leave a comment, subscribe, do all of the usual YouTube things. There's also buttons you can press if you're watching on Twitch to make stuff happen. It really does help boost engagement, and I appreciate all of you who take time to press buttons and make stuff happen. It is really good. I see we have a bunch of the regulars coming in here. We have David Howden, Sophia, Nina. Great to see you live this time. Thank you for being here. Always nice to have you. Prath, James, John, Paul. Great to see a lot of the regulars tuning in, as always. Coming from Paul here, you got an extra hour today because daylight saving time ended. So you got an extra hour. I know in the US you changed your clocks today. We changed our clocks a week ago. So now we're back in sync, which is more convenient when planning meetings because this week of non-synchronized time is really weird. I have I have a lot of meetings that involve people in the US, and the last week people have been sending out reminders like, if you're in Europe and your meeting is organized by the US people, your meeting will be earlier or later. So now at least we don't need to do that. Of course, there are some countries in the world that don't do daylight saving time. They figured it out. So then there's always some people that have to remember which time we're doing. But at least now we can forget about daylight saving time nonsense for another 6 months, which is good. Okay, so as always, this is an interactive stream. You people can ask me anything you want, and I will do my best to try to answer those questions. If you don't have questions, I get to choose what we chat about, which usually means chatting about my favorite topics in the universe, which is also what we're going to do until the questions flow in here. Just want to make a comment. Some of you might remember that in last week's stream, there were a couple of trolls, and the stream got a bit disrupted at some point. But thank you to everyone who stuck through that. We resolved it. It's fine. It's all taken care of. Thank you. And also, thank you to everyone who reached out for me after the stream last week. So some of you noticed that I was a bit rattled by some things happening in the comments. And a couple of you reached out after the stream to check on me. And thank you for that. I really appreciate it. I really appreciate that you all reach out. And, it reminds me that this is a community and we're all in this together. And I really do appreciate those of you who took time to just message me last week. It was much appreciated. As always, whenever you message me, I'm always like, hey, someone got in touch. This is cool. I might not always reply to your emails, but I do read them and I do appreciate all of them. Hey, Scott, great to see you here as well. We have David Howden here as well. DST presumably makes even less sense in tropical countries. Yeah, it's also weird. Like, I grew up in Spain, and Spain is already in the wrong time zone because they technically should be in the same time zone as the UK and Portugal, just geographically. But at some point, they decided to be in the same time zone as the rest of mainland Europe, which makes no sense because then when you're in Spain in summer, you sometimes feel like the time zone just doesn't completely align with what it should align with. And then when daylight saving time happens or when we change the clocks, it just feels even weirder. But yes, some countries don't do this anymore, and you'll know that I would be very much in favor of not doing that as well. Comment from Nina, I still think we should all stick to standard time and stop changing our clocks every 6 months. Absolutely agree. It doesn't make any sense in modern society. It made sense in the time it was implemented. It doesn't make any sense now. Hey, David Dunn, great to see you here as well. Yeah, everyone complaining about daylight saving time, but as Scott says, the real culprit here is Earth's axial tilt. See, the Earth is tilted. That's not something we can change. We just have to deal with it. But dealing with it by changing our clocks every 6 months is an interesting choice. Not one that I necessarily agree with. I feel like there's a lot of dust in the air today because I moved some furniture around and now I just feel like there's a lot of dust in the air. But this is why I always come prepared with water and tea to help me through this. Okay, so let's jump straight into some core physics. As always, ask me questions and I will try to answer them. Until you ask me questions, we get to talk about some of my favorite things in the universe. For an example, the cosmic microwave background radiation. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. So basically 13.5 billion years ago from our perspective. What we're looking at here is really an image of the first light in the universe. And for anybody keeping track, it took less than 7 minutes today. I needed to make up for last week, where you did not see the CMB, the cosmic microwave background radiation, until later on in the stream. So, cosmic microwave background radiation is... Why is my chair sliding by itself? Weird. That is not related, but my chair is just... has a weird slide today. Okay, never mind. I will figure out why my chair is sliding later on and guess one of the wheels is messed up. Okay, interesting discovery. He's suddenly seen me slide off screen. It's because this chair has just started moving more than it should. Anyway, what you can see here is the CMB, the cosmic microwave background radiation. So in the very, very, very early universe, we had four main components. We had dark matter doing its own thing. I'll get back to dark matter in a minute. Then we had protons, we had electrons, and we had photons, particles of light. In the early universe, everything was chaotic. These things were bumping into each other constantly. Not dark matter. Dark matter was doing its own thing. But protons, electrons, and photons were constantly bumping into each other. As the universe gradually cooled down, protons and electrons could combine together to form the first atoms of the universe. At this point, the photons, the particles of light, can no longer interact, and so they break away. These photons, these particles of light, have been traveling freely throughout the universe ever since. And when we look at them today, they're everywhere in the universe. Due to the expansion of the universe, the wavelength of these photons has gradually been shifted towards a microwave range of the electromagnetic spectrum. So today it is a cosmic background that is everywhere in the night sky, and it is in the microwave range of the electromagnetic spectrum. So we call it the cosmic microwave background radiation. And you might see here that there are orange and blue spots. This is the overall temperature of these photons. Now, we know that the background of the universe is at an average temperature of 2.73 degree Kelvin, which is minus 270 degrees Celsius and minus 440 degrees Fahrenheit. But on top of this base temperature, there are tiny, tiny, tiny temperature differences of the order of 1 part in 10,000. Sorry, 1 part in 100,000. And these are tiny, tiny regions that are slightly warmer or slightly colder. Here shown with the slightly warmer colors with the red, the orange, and the slightly colder colors with the blues. Now, by looking at how this map behaves, how many red spots there are, how they're distributed, we can get a snapshot of the statistical properties of the early universe. This is very, very cool. This is a photo of the baby universe. And we can use that information to figure out 6 main things: the age of the universe, how much dark matter there is in the universe, how much dark energy there is, how much normal matter there is, and when stars began to turn on, and also... Okay, that noise is not in my apartment. There's like a loud drill, but it's not in mine, it's up there. Yes. Then there is also 2 parameters telling us how the universe looked after the end of inflation. This is what we can get from the CMB. So by looking at this map, we can figure out that the universe has 3 main components. Everything we see, everything we're used to, everything from the stars you see in the night sky to me, to my teamwork, to that annoying drill. All of this is normal matter. Normal matter only accounts for 4.9% normal matter. 4.9% of the energy budget of the observable universe. There is another 26.2% that is in the form of dark matter. Dark matter is this weird type of matter that is driving... Dark matter is this weird type of matter. See, this is the problem when I do explanations and also pilot that brain and mouth don't agree. So, normal matter, 4.9% of the energy budget of the observable universe. Then there is 26.2% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact electromagnetically. This means that as far as light is concerned, dark matter is not there. Dark matter does not emit light, it does not absorb light, it does not reflect light. It is essentially invisible matter. Then the remaining 68.9% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It is pushing everything away from everything else. And that is pretty much everything we know about dark energy. So this is very, very cool. We get these numbers from the CMB. We get this 4.9, 26.2, 68.9%. We get these exact numbers from the cosmic microwave background radiation, which is what you saw on the previous image. And this is really fun because I say I'm a cosmologist, I study the universe, but we don't know what dark matter is, we don't know what dark energy is, so there's 95% of the universe that we don't know much about. But we know that we don't know much about this 95%, which is already quite an accomplishment. This allows us to make very fun jokes and comments because most of the universe is indeed dark. We have dark matter, we have dark energy. So then we can say that our universe is dark and mysterious, but it's not unknowable. We can study dark energy, we can study dark matter partly via the cosmic microwave background radiation, this amazing thing here, but also through the distribution of galaxies and how this distribution has changed over the course of the universe. Because if we consider that dark matter is 5 times more abundant than normal matter, dark matter is in a sense setting the scaffolding for other matter in the universe, while dark energy is then telling the scaffolding how to change over time. So by looking at the distribution of galaxies today, we can figure out what dark matter is doing today. By looking at the distribution of galaxies in the past, we can see how this has changed, so we can understand how dark energy is affecting the structure of the universe and everything else inside it. And in order to get this idea of what galaxies looked like in the past, we just look further and further out in the universe, because it takes a long time for light to travel towards us. So the further out into the universe you look, the further back in time you're looking. So ideally what we want to do is we get amazing telescopes or satellites that can map the distribution of galaxies going further and further and further back in time, or further more and more and more distance. And then you get an idea of this is what the universe looked like at different ages, different epochs, and then you have these kind of snapshots, you put them together and you get an idea of what dark matter is up to and what dark energy is up to. So we get to make jokes around Halloween of what is dark and mysterious in the universe, pretty much everything. The main dark and mysterious things in the universe are dark matter and dark energy, but even though they are dark and mysterious, they are not unknowable. We can actually try to study them, which we do via the cosmic microwave background radiation and via galaxy surveys. And also, there is a comment here by Scott, does dark matter bend light? It does. Because dark matter is a big gravitational object, it is going to distort the fabric of space-time. It is going to curve space-time. Anything with mass curves space-time. The curvature of space-time tells objects how to move. So even though dark matter itself does not interact with light, dark matter can curve space-time, and then the light beam traveling throughout the universe is going to feel the curvature of space-time and is going to get deflected due to the presence of dark matter. So even though even though dark matter doesn't interact with light directly, it can still affect light. So another thing we can use to study the universe, to study dark matter and dark energy, is how much light is getting distorted. Because if we see that light is getting bent around something, but we can't see the something, it's probably dark matter. So that's something else we can use. This is known as weak lensing or galactic lensing, whereby light from distant galaxies is distorted by something big and massive that we don't see, and that is dark matter. So this is another way that we have trying to study dark matter and dark energy. Okay, this was just a big dump here of some of the things that, just some basics of the universe. We're going to go in more in detail. I see there are a bunch of questions coming in now, so I'm going to jump into all of these questions. But just sticking to what I'm saying here, Scott made a comment that known unknowns are fine. It's the unknown unknowns that are dangerous. Exactly. You know, we know that the universe has 95% of it that we don't know much about, and this is already a huge achievement. The fact that the fact that we know for sure that the universe has dark matter and dark energy is amazing. We don't know what they are yet, but we know that we don't know this. However, there's going to be a lot of other things in the universe that we don't even know that we don't yet know about. We don't yet know that the things that gaps in our knowledge. So that is very, very cool as well. Okay, Scott quoting the Donald Rumsfeld epistemological framework there. Yeah, I did notice about the known unknowns. That is a reference to philosophy, which is something that was one of my favorite subjects. And I almost became a philosopher and then had a very influential philosophy teacher who told me that I'd be better suited to become a physicist. And just based on the aspects of philosophy that I enjoyed, he recommended that I go into physics instead. And it was an absolutely correct decision. But I do love philosophy. Also, why anytime I make comments about absolute truth, I will then point out explicitly that science does not deal with absolute truth. Science deals with empirical truth, and there's a difference there. And the part of me that studied philosophy will make sure that I get that correct. Okay, so there's a comment from John related to what I was saying about dark matter and dark energy. And I know there were 3 other questions before about JWST, about wormholes, about matter and antimatter. I will come back to those in a minute. But sticking with dark matter and dark energy, also, we are 16 minutes in, and I have already answered the 3 prompt questions I wrote in the caption of the YouTube video today, almost as if I deliberately chose those questions because that's how I wanted to start the stream. It's the advantage of being the one in charge of the streams, that I get to choose what I put there. Question from John. Have you seen the new study supporting the idea that dark energy is being caused by black holes? I think it was based on DESI data. I have not seen that, John. If you have a link to it, please do share it. I would like to look into that because there's often the idea that black holes could be causing dark matter, but I've not seen the idea that black holes could be causing dark energy. That is interesting. I will have to read up on that because it's not something that right now I have anything to say upon, but it sounds very cool. So just quick recap here. Black holes are regions of the universe that are so dense that nothing can escape, not even light in a vacuum. Or sorry, not even light. As we know, nothing in the universe can travel faster than light in a vacuum, therefore nothing can escape the gravitational pull of a black hole. Black holes have several different ways of being formed. One of them is a star reaches the end of its lifetime. It collapses, because in a star you have a constant battle between pressure pushing things outwards, gravity pulling things inwards at some point. When you run out of elements to burn in the star, it can gravitationally collapse, and first it will explode as a supernova, push out its outer layers, and what you're left with is a black hole, which is a region of space-time that has a huge gravitational pull, and this gravitational pull means that once you get close enough, you cannot escape. Good thing is that black holes are gravitational objects, which means if you're far away from a black hole, you don't need to care about it, but as you get closer and closer, you're going to feel the effects more and more. Another way you can form black holes is if you have a region of space-time in the early universe that is so dense it can directly collapse to form a black hole. This is what we call a primordial black hole. And there has been a lot of ideas of, given that we can't see black holes because nothing escapes from a black hole, we can't see black holes. Could black holes account for the dark matter? Generally, we don't think that stellar mass black holes can account for the dark matter. However, there are some ideas that primordial black holes, or black holes formed in the very, very early universe, if they exist, could account for part or all of the dark matter today. So primordial black holes are often considered a dark matter candidate. However, the question was, have I seen a paper linking black holes and dark energy? And to that I have to say no, not yet, but I will absolutely look into that. I've made a note of it in a very cryptic way that will not make sense to me once the stream is over, but that sounds cool, so I'll try to look into that. That does sound like a cool thing to look into. Okay, now I'm going to go back to the top of the comments and answer the questions that I saw coming in about wormholes, there were a few cool questions coming in. I saw one about wormholes, 2 others that I want to go back and answer. Before jumping back to the top, there's a question here from Guadav. How's everyone doing? Let me know in the comments, how's everyone doing? Did you have a good Halloween? I hope you're all doing well. Follow up from Guadav, how was Halloween for you? Halloween for me was a bit mixed. It's honestly been a bit mixed. This week has been incredibly hectic at work. And I have a lot going on right now, which has just made it a really busy week combined with not sleeping well. I just felt like I was really tired this week and not at my best. But then Halloween, I love Halloween. I'm a sucker for Halloween. And I did have 2 parties that I was planning on going to. In the end, I pulled out of one of them because I do need to manage my energy levels. I am chronically ill, and I realized that going to both would have been a bad idea, so I dropped one of them. But the one I went to was the office Halloween party that I organized, and that was super fun. I have a costume that I made last month, which is a mushroom witch. So it's like if you imagine a witch but that looks like a mushroom, and it's a very cool and very cute costume. And I got to use it again for the Halloween party, which was really nice. The Halloween party at the office was really fun. And then yesterday I made pumpkin soup, which just feels very Halloweeny. So yeah, overall I think it's been a mixed bag, but I think Halloween was fun. But now it is officially November. Halloween is over. Helsinki has its first snow. It's a light dusting, but we have snow, which means it's almost Christmas. And I have already 2nd of November, so yesterday I already heard Mariah Carey announcing the return of Christmas. I already heard that Christmas song on the 2nd of November. It really is true that Halloween is the last front against Christmas coming earlier and earlier. The goths are there. The goths and the gays are holding back Christmas by promoting Halloween. So please do celebrate Halloween, because it's the only thing keeping Christmas at bay. But now it's November, so now we can fully embrace winter and Christmas. Christmas is coming. Very ominous. Okay. Comment from Paul: Halloween lasts till Thanksgiving. I approve of that. I think having a month-long Halloween is a good approach. Yeah, why not? That sounds fun. There's a fungus with the vernacular name witch's butter. I have heard of that, yes. See, when I was planning my witch's mushroom outfit, so the story behind the mushroom witch is last month I went to a costume party that had the theme Harvest Witches, and I decided that, late October, what are you late September, early October, what are you harvesting? Mushrooms. So then I was looking into how I could make a witch mushroom outfit, and I was looking at different witches. And then I realized there were different mushrooms, and then I decided to just paint myself like one of the typical toadstool amanitas. It's red and white spots. And I made a hat that looks like a witch's hat, but it's painted like a mushroom. I briefly considered putting on my mushroom witch outfit for the stream today, and then decided against it. But yeah, the mushroom witch hat is very, very cool. It's Halloween and Diwali together here. It is indeed. Happy Diwali to everybody who is celebrating. I know it's a big festival, and I hope you all had a lot of fun with celebrating that. Scariest costume, death and taxes. Yeah. There's always scary costumes you can come up with. At the office Halloween party, we also put something on the board where we add your scariest physics here. People wearing the usual things. If you've got a missing factor 2, your code's broken, reviewer number 2's come in. And then it got a bit dark and someone was like, nuclear reactors malfunctioning. I'm like, okay, that is indeed scary. It was a very fun Halloween party. Half the people at karaoke were in traditional wear and the other half were in Halloween costumes. That sounds amazing, Prath. That sounds like a really cool party. Also, I love Indian traditional outfits. I got to wear some when I was in India last year. I just love the colors and how bright and vibrant everything is. So a combination of those outfits and Halloween costumes sounds like a blast, actually. That sounds like it was really fun. Hope you had a good time. And karaoke is always a laugh. I love karaoke. Comment from David: there's a Christmas link there's a Christmas link to that mushroom type, so you can reuse the costume in December. I can. It would not be very difficult to make this now into a kind of Santa witch. It's very close to being a Santa witch. So I could turn my mushroom witch into a Santa mushroom witch. That is going to happen. Yes. Okay. Scariest physics 3D time. Yeah. Let's rederive all of general relativity because someone wants 2 time dimensions. Scariest physics. What happens with white holes and Hawking evaporation? Those are fun conversations that we've had thanks to questions here on the stream. There's also a comment here from Scott when I was talking about black holes. It's not possible for a star to be massive enough to become a black hole without going through the right processes because of density, right? Yes. So just having a massive star is not enough to say, okay, you have a black hole. There's a whole process that needs to happen in order to trigger the formation of a black hole. Also, you can have stars that reach the end of their lifetime and explode as a supernova and then collapse as a neutron star or as a white dwarf. So not every massive star is going to end up being a black hole, but there are thresholds. If it's above a certain mass, it's going to end up as a black hole. If it's in between, it will be something else. but it also needs to be at specific parts of its stellar evolution. This is how you end up with red giant stars as well, that not that different phases of evolution. So yeah, generally, the main criteria for a star to become a black hole is the mass, but there's some caveats there. Okay, scary physics, vacuum decay. Yeah, see, somehow most of the physicists I know don't think of the vacuum decay as being scary. And I think the reason is because if vacuum decay happens, you won't know about it. We would just, it's literally like Thanos snapping his fingers, we just, I can't believe I just made a Marvel reference. Damn. All of my comments about not liking superhero movies, and the first reference that came to mind was a Marvel one. Yes. So the thing about vacuum decay is the universe could literally just end at any second without any warning, but there would be no warning, so you wouldn't see it coming. So it's not really scary, right? We just stop existing. There won't be enough time to be scared about it or to know that it's coming. It's just done. The universe is over. Reset the universe. Let's try it again. But generally, we don't think vacuum decay is likely to happen. So it's something that I think in general, physicists aren't overly scared about. It's a fun thing to think about, but it's not overly scared about. It's overly worrisome, I think. Comment from Gwedov. Scariest physics, MOND is how gravity works. I mean, if we find enough evidence for MOND is modified Newtonian dynamics. It's the idea that you don't need dark matter to explain the way the universe works. It's just that we haven't understood gravity well enough. Unfortunately, no model of MOND, of modified Newtonian dynamics, is able to explain the CMB, the cosmic microwave background radiation. The day we find a MOND theory that can explain this, then I'll believe it. But until then, MOND is very good at explaining the motion of galaxies, but it is not a complete explanation in the way that dark matter is. Of course, dark matter is not perfect. This is a good infusion. Dark matter is not perfect. It's just the best model we have so far. Okay, so now I'm going to go back to the top and answer the 3 questions that came in not long after we started. Where were we? Let's see, going through the questions. We complained a lot about daylight saving times, yes. Okay, up first, question from Paul. If stable wormholes exist to connect 2 points in space, how can they do it by bending space if that same space is otherwise bent or shaped in a different way by normal gravitational objects within? Whew, okay, excellent question here. So, a wormhole is a hypothetical construct that connects 2 disjoint parts of space-time. And the way we generally think about it is imagine this is space-time. We imagine space-time to be a sheet, even though it's 3-dimensional, but let's just imagine space-time to be 2-dimensional for now. So imagine you want to connect this point and this point. What a wormhole does is it basically bends it so that you can do that. However, it is not really bending all of this. It is creating kind of a curvature around here that does not affect everything else here. So even if we had a wormhole, this hypothetical concept that connects these 2 points where my fingers are in space-time, while it essentially does this, and this is the way we usually portray it, it's not actually this part that is bending. It's the part that you don't see that is being bent. So it is quite difficult to conceptualize a wormhole because generally we think that it's just joining 2 random points in space-time by distorting space-time. But then that leads to the idea of what is happening to the space in between. So as Paul's question here, if a stable wormhole exists to connect these 2 points, how can they do it by bending space if that space is otherwise bent or shaped in a different way? So normal space is affected by normal objects, by gravitational objects, as we'd expect. But then there's these 2 points that are basically connected, but not directly connected in the sense that all of the universe is bending to connect these points, but rather there is some curvature that is allowing these to connect. Now, wormholes are one of those things that are a solution to the Einstein equations, to the equations of general relativity. So it is something that theoretically could exist. However, it's something that physically we haven't been able to realize yet, and it's not something that we can make happen. It's not something that we found, and we don't know if wormholes occur naturally in the universe, or if it's just a mathematical quirk of general relativity. Now, even if a wormhole did exist, usually these are considered to be unstable. So as soon as any matter tried to go in a wormhole, the wormhole would collapse. So while in sci-fi it's very cool to use wormholes as a concept for space travel, in reality it's not something that we think would work, because as soon as something enters this kind of forbidden region that is curved, that's connecting these 2 points, the wormhole would collapse. The energy of the wormhole cannot sustain something going through it. So wormholes are a very cool hypothetical concept that probably don't exist in reality. But even if they did, and they were stable, the thing they're bending is not the entire fabric of space-time. It's just kind of joining 2 points that were not previously joined via some type of curvature, but that doesn't mean they're curving everything in between those 2 points. Hope that answers your question, Paul. That is a very cool question, by the way. Just a comment to everyone. Today, the stream is going back to its old format of being 1 hour, because that was what the stream has been. Cup of Cosmology is now in its 10th year. For most of this time, it has been 1 hour streams. For the past 6 months, I've been doing 90 minutes, 100 minutes, 80 minutes, somewhere like that. Today, I am capping it at 1 hour. So today, it is only a 1 hour stream. We are not going to do more than 1 hour today. The reason being, I have a bunch of important stuff happening tomorrow, and I really need to make sure I get a good night's sleep, and that I actually am well rested and recovered tomorrow. So today we are capping it at 1 hour. And I just saw a very cool comment here from Scott. I've heard it called an Einstein-Rosen bridge. Can you tell us about Rosen? I should be able to tell you about Rosen, and I'm currently blanking on Rosen. So, an Einstein-Rosen bridge is a type of wormhole. It's not like all wormholes are Einstein-Rosen bridges. It's just a type of them, and it's about how you go about implementing them mathematically. So, according to a very quick internet search, Nathan Rosen, the Rosen in Einstein-Rosen, was an American and Israeli physicist noted for his study on the structure of hydrogen molecules and his collaboration with Einstein and Podolsky. Okay, so that's who he is. He's a physicist who was around in the early 20th century and who contributed to general relativity. That makes sense. It's a name that was somewhere in the back of my brain, but I couldn't remember directly. Okay, more sticking with the wormholes. It's inevitable that if we bring up wormholes, there's going to be a lot of discussion and conversation. Comment from Prathia. Don't wormholes require negative mass or energy to allow mass to go through? Yes, indeed. So one of the reasons that we say that wormholes are unstable is by construction, they cannot contain more mass than what they already do. And if you add, if we go back to this idea here, if we're connecting these 2 points by kind of making a bridge between these 2 points, this bridge is going to be not really part of normal space-time, but a curvature in addition to the existing space-time. So if you put any mass going in there, you're going to disrupt the overall amount of energy that we have contained in space-time. So to compensate this, you kind of need to have the wormhole having negative mass to account for the excess mass going around. So one of the reasons why, mathematically speaking, these these wormholes are not expected to be stable, is because the way we construct them mathematically, it's going to have some negative energy or negative mass in order to explain how things are working. So comment from Paul here, it's like a rickety bridge that falls apart as soon as you step on it. Yeah, in general, if you happen to see a wormhole, I mean, first of all, congratulations, you're the first one we know of to ever do this. If you do see a wormhole, maybe don't fly your spaceship into it, unless you figured out wormhole technology like John Crichton in Farscape, in which case, go for it. If you want to slingshot around the planet and create a wormhole and jump into it, if you know what you're doing, go for it. But yes, in general, if you see a wormhole, maybe don't fly through it. Okay, I see there's more comments here about dark energy and dark matter. 1 hour stream only today, all future streams, 1 hour today. Future streams will depend on the week. I do like the 90-minute format. It lets me talk about a lot more things. And usually I don't aim for specifically 90. I just, once we reach the 90-minute mark, I'm like, okay, I'm going to stop. But today I really do need to make sure I save energy for tomorrow. I have kind of a new role at work. I'm still a postdoc, but I've gotten a new role that involves a lot of responsibility. It's related to Lisa. I'm not going to tell you too many details about it now, but tomorrow I have a meeting that I'm supposed to be leading related to this, and it's a tiny bit scary. So, and I also have two other meetings tomorrow related to this. So I do need to make sure I'm well rested for tomorrow, which means today we're capping it at 1 hour. We'll see if I stick to that. The plan is 1 hour today. Okay. Comment from David, and now if your time is already very generous, thank you. Thank you for the comments. Okay. What happens when a wormhole collapses? Sticking to the wormhole questions. I know there's still some other questions that we need to answer, but sticking with the wormhole question, what happens when a wormhole collapses? We don't know completely. It's the same thing as what happens inside the event horizon of a black hole. We don't really know. Then there's the idea that often you can consider the ends of a wormhole to be a black hole and a white hole. So a wormhole would essentially connect, like, everything that falls into a black hole could be connected via a wormhole to a white hole. So then talking of what happens inside a wormhole is as difficult as talking about what happens inside the event horizon of a black hole. It's something that mathematically becomes very difficult to describe. So what happens when a wormhole collapses? We're not sure. What would happen to any mass that or matter that has jumped into said wormhole when it collapses? We're not really sure. It's something that mathematically becomes very difficult to describe or very difficult to talk about. We just have the idea that a wormhole cannot contain mass or energy, so if it does, it would cease to exist. What happens to the stuff that jumped in? We don't know. Okay, comment from John, sticking with wormholes. Would there be gravitational time dilation effects going into a wormhole? Absolutely. If we think about a wormhole as basically being an extreme curvature space-time, you will have all the usual gravitational effects that you get when you curve space-time, which are time dilation, length contraction, so time goes slowly to whoever's getting thrown into the wormhole. Lengths behave in a weird way. Then there's the question of, would you experience spaghettification if you jump into a wormhole? Probably not, because it's not a big gravitational object, but it has the same curvature as a big gravitational object. So it becomes quite weird. But you would absolutely have gravitational effects like time dilation going into a wormhole, because you'd have a huge curvature of space-time. And we know that this curvature of space-time is what causes the effects of time dilation, where time behaves differently for people on very curved parts of space-time. So yes, jumping into a wormhole, you would indeed get this kind of time dilation. Black hole, white hole makes it sound like one direction of travel only. Indeed, it does. And depending on how you mathematically describe a wormhole, all of the descriptions are solutions to Einstein's equation, as are black holes. But the way you describe the black hole, you can end up with, the wormhole, you can end up with a wormhole that only allows for one direction of travel. But again, what does direction of travel mean if as soon as you get inside a wormhole it collapses? There's no direction of travel. No travel is allowed. So it's not like there's a direction, because you can't travel anyway. So yeah, it's very cool. Sticking with wormholes, I love the wormhole questions. Keep them coming. We all know that any person that disappears into a wormhole, never to be seen again, will inevitably show up in a later season. Absolutely. And I think this is a cool thing, because there's a lot we don't know about wormholes. It's a cool thing to throw around in sci-fi. This is something I love about sci-fi. I feel like sci-fi is the fanfic of science. You know, anytime there's a TV series or a movie or anything you like, there's going to be fanfic of it. And the fanfic usually relies on filling in plot holes or things you didn't like about the original. I love fanfic. You know, it's a way for fans to show appreciation of the source material. And I feel like, in a way, sci-fi is often fan fiction of science. And this is what I like about sci-fi, that it can pull up elements that we don't have an explanation for. We don't really understand wormholes, so you can throw it about in sci-fi. What then annoys me is when they kind of change the headcanon. You know, if you're doing fanfic, you can't rewrite something that has happened in the main source material. You can fill it, you can elaborate on it, you can modify it slightly, but you can't change main headcanons. Not headcanons, main canons. It's not even headcanon, it's main canon. So I feel like this is my problem with sci-fi. This is a tangent here. My problem with sci-fi is when they take something that we do understand in physics and then try to make it weird. For an example, reversing the polarity of the neutron flow. Neutrons do not have polarity. I'm sorry, Doctor Who, that's not how it works. Ah, reverse the polarity of the tachyon flow if you want. We don't know if tachyons have polarity, sure. Neutrons don't. You can't reverse the polarity of the neutron flow. Anyway, Doctor can get away with it. But this is my point. Sci-fi is fanfic of science. This is why I like sci-fi, as long as it doesn't change my canon. Yeah, well, that's a random tangent that we just got onto talking about wormholes. Coming from Paul, a book I read and then forgot the title of. They created two wormholes together, then dragged one at relativistic speeds to another star system, so it was connecting 2 points in time and space. Well, that sounds cool. I'm not sure how feasible that is. How do you drag a wormhole at relativistic speeds? That sounds cool. If you remember the book, Paul, do let me know that I can add it to my long list of sci-fi books that I want to read and probably will realistically never get around to. Okay, so when I started the stream, I went on the brief summary of CMB and dark matter, and 3 questions came in. We've just finished answering the first of those 42 minutes in. I know there were 2 others. There has also been some follow-ups. For now, I've just focused on the wormhole questions. Okay, so back to the top. Where were we? We just answered the question about wormholes from Paul. At the same time, or within seconds, a question literally 1 minute later, a question from James came in regarding cosmological thinking being tested with the findings of JWST and other. Is there any event upcoming that will help us answer this question? Lovely question there, James. So there's a lot of stuff going on right now in the universe. Obviously, there's always stuff going on in the universe. There's a lot of stuff going on right now in science, in cosmology and physics. One of the big things that we have is the JWST, the Just Wonderful Space Telescope. There is no other name for this telescope. This telescope is peering back our cosmic evolution and looking at really old galaxies, really old stars. It's helping us understand how stars form. It's getting a lot of data, and some of its data is not what we expected. And this is very cool. It is challenging some of our ideas about how galaxies form, which is very cool. There is also ongoing right now Euclid. Euclid launched last year. It is a European Space Agency mission that is trying to figure out dark matter and dark energy by creating a detailed map of the evolution of the universe, or of dark matter, or the structure of the universe going back further and further in time. Euclid is expected to give us first data already within the next year or 2. We already have some preliminary data. There are some cool images, but the first science results, where they should hopefully shed some light on dark matter and dark energy, we can expect within the next 2 years or 18 months. We also have ongoing DISI, the Dark Energy Spectroscopic Instrument, which is a ground-based telescope, very complementary to Euclid, staring very deeply at one patch of the sky, like a broad patch of the sky, but not like Euclid, which is doing most of the sky. And DISI is also creating a detailed 3D map of cosmic evolution. We already got the first results from DISI last year. Not last year, 4 months ago. Sorry, 4 months ago. And they found hints of dark energy not behaving the way we expected, which is very cool. So we have all of these things coming up. We're going to get more data from DISI. We're going to get data from Euclid. We have JWST. All of these can challenge our standard model of cosmology and can shed light on what is happening. And they're all very complementary, so the information we get from them can be used together, which is also very nice. So what is upcoming? They're like an event that is upcoming. I think that was the question. Let me just reread the question. Is there any events upcoming that will help us answer this question? I'm guessing this question is just like, how much do we trust our standard model of cosmology? And I think all 3 of these missions might help. There's also some new weak lensing data expected soon, which might also help with some things. So yeah, I think within the next 10 years, we're going to get a huge amount of information from different cosmological missions. And it's really going to help us kind of dig down on, is our standard model of cosmology an accurate description of the universe? So very cool question, James. Okay, I'm currently stuck on all comments or whatever's coming in right now. I'm not seeing. I will scroll back down in a minute. Question from Prath. You know it's going to be a difficult question. Here's the antimatter-matter question you've been sitting on for 2 weeks. What if we have more matter than antimatter because Hawking radiation from primordial black holes release more matter than antimatter? Excellent question there, Prath. And I saw that someone later on in the comments said that I've written a paper about this. This is true. I have written a paper about this topic. So in the early universe, there was matter and there was antimatter. Antimatter is like matter's evil twin. It's equivalent. It has a lot of similar properties, but it has opposite quantum numbers. So if you have matter with spin up, you're going to, or with positive charge, you're going to have antimatter with negative charge. When matter, every matter particle has its antimatter correspondent. For an example, an electron, the antimatter partner of an electron is the anti-electron, also known as a positron. We know that if matter and antimatter meet, it annihilates and produces radiation, produces photons, particles of light. So if matter and antimatter had been created in equal quantities in the early universe, then everything would have annihilated. And the universe today would just be photons, particles of light, and nothing else, because all matter and antimatter would have annihilated in the early universe. However, for every 1 billion particles of antimatter, there was 1,000,000,001 particle of normal matter. So a lot of the particles and antiparticles did annihilate in the very, very early universe, produced a huge amount of photons, which incidentally are the photons that make up the CMB, the cosmic microwave background radiation. These are the after effect of matter and antimatter annihilating in the early universe. You get 4, 5 CMBs today, can't complain. But it's good that there was more antimatter than matter. However, we don't know why this was the case. So every antimatter particle found a matter particle annihilated, but left us with a small fraction of matter, which today makes up everything we know of in the universe. So the question of why was there more matter than antimatter in the early universe is one we don't have an answer to. And it is a big open question in the field of how do we solve the matter-antimatter symmetry. So there is the idea, if you have primordial black holes, which I mentioned before, are these black holes that are formed in the very early universe. As far as we know, black holes could have something known as Hawking radiation. Hawking radiation is where you produce two particles on the event horizon of a black hole, a particle and an antiparticle. One falls in, one gets shot out. It's not directly gets shot out, it gets caught up in the gravitational pull, slingshots around, and then gets shot out of the black hole. It's a very cool effect. But this basically means that the black hole loses something due to Hawking evaporation. Now, this particle is not escaping from inside the black hole, but it is being pair produced on the event horizon and flies out. To compensate for the particle that escapes, the black hole loses a bit of mass. This is known as Hawking radiation. Now, the particles that are produced and come from Hawking evaporation could be any particles. They don't have to be standard model particles. They could also be dark matter particles. So then there is the question of if we have primordial black holes in the early universe, these black holes that are formed when a patch of the universe collapses to directly form a black hole without going through the whole stellar evolution stage. If you have this in the early universe, could you then have Hawking evaporation of these primordial black holes? And could this Hawking evaporation then produce matter and antimatter? Cool. So short answer to this is yes. You need a lot of things to be true here. You need primordial black holes to exist. You need these primordial black holes to decay via Hawking evaporation. And then you need it to be along specific channels that produce the right amount of matter and antimatter symmetry while not messing up anything else, because the dark matter is also, the primordial black holes will also decay potentially along different channels. This is different possible ways they can emit Hawking evaporation. Now, you can't have too much of this or you mess up things like the amount of particles, the amount of matter and antimatter we've seen today. You also have to bear in mind that if you evaporate them too quickly, you're going to affect how much radiation there is in the universe, which we would then see in the CMB. If you produce, so there's a lot of constraints on how you can do this. But if you have primordial black holes, and if these have Hawking evaporation, and if this Hawking evaporation produces matter and antimatter in a specific range, it could somewhat contribute to an explanation of matter-antimatter symmetry. Long answer. The conclusion here, Prath, is it's a very cool question. It's a very well thought out question. Yes, with a lot of caveats. So yes, we could potentially explain the matter-antimatter symmetry with primordial black holes evaporating, but you need a lot of criteria to be met in order for this explanation to happen. But that is indeed something that I have worked on. I have a paper where we're not so much interested in the matter-antimatter, or at least I wasn't so much interested in that question. But what we were asking is if these primordial black holes also that are evaporating in the early universe, if these produce the dark matter that we see today, can we then use what we know about dark matter to constrain how these primordial black holes could have evaporated? And the answer is yes. And as a byproduct, we also calculated this matter-antimatter symmetry thing. So, Prath, if you want to read about that, I can link you to the paper. And just a comment here. Anytime you try to find a scientific publication, you're probably going to be hit by a paywall. Okay, I'm back to the bottom of the comments, just in case anyone wants to put fresh comments there, though I think the comments have gotten stuck, but that's fine. So there is a whole peer review system. It's been a while since I've done a rant about this, where we publish papers. So we submit papers to journals. These then get peer reviewed, which is a very important aspect of the papers being published. And then eventually, once the peer review has gone through, the paper gets published in the journal. Now, this is something that a lot of people might not know, but we do not get paid extra for our publications. It's part of our job. So it's not in the sense that I've authored a publication, I'm going to get money if more people read my publication. That's not how it happens. However, most scientific journals charge a fee to publish a paper because a lot of scientific journals are actually ran for profit. Not all of them, but a lot of them are for profit businesses, which means we pay a fee to publish. And then the articles are behind the paywall and people have to pay a fee to read them. You'd think that that fee would come back to the authors, the editors, the peer reviewers. No, it does not. It does not. That fee goes to hosting the paper and publishing the paper. So, point being here, if you ever find a scientific article that is behind a paywall because you need to pay to access the journal, most universities subscribe to these journals, so then I can access my papers because the university pays for me to access the paper that I wrote and that I paid to publish, not me directly. The university pays for me to publish the paper and then pays the journal for me to be able to access the paper that I wrote. It's a broken system. But my point here is if you ever find a paper that some scientists have written that is behind a paywall and that you really want to read, email the scientists because chances are they will just send you a PDF. This is true if anyone wants to read my papers. I can link you to the open access version or the publicly available version because all of my papers are also publicly available somewhere. So generally, if you're hit with a paywall, contact the scientists and you might get a copy. Also, I am not going to promote certain sites that have paper that remove the paywall of papers, but these sites exist. And they exist because the whole system is broken. We pay to publish, we pay to access the papers, and then everyone pays to access the papers we publish, and we don't get paid for the papers we publish. It's part of our job, which is fine. I'm not saying we should get paid for every paper. That would make the whole publish or perish thing even worse. But you have to ask the question of if publishing in a journal costs 1,000 something euros per paper, where does that money go? Yeah, you had to pay to read your own paper. Yeah. There was a funny situation when I was in Brussels that one of the journals that I published in, my university had stopped. The university in Brussels at the time wasn't paying the subscription for that journal, which meant the final version of the paper that appeared in a journal, I could not access via my own university credentials. So I could not see the final published version of my paper, my own paper, unless I paid. It was like, I literally sent you this paper. I know what it looks like because I sent it in. But yes, if your university doesn't subscribe to the journal, you might hit the paywall and not be able to access the final product that you produced. Which is yay. There are journals pushing for open access so that people can read it and that people don't pay to publish. But it's a slow process. Okay, so I answered the three big questions, the wormhole one, the matter-antimatter symmetry. Point being there, Prath, if you want to read that paper and you can't find the open access version, ping me on one of the platforms and I will send you the PDF of it, because there's no need for you to pay to read the paper that I wrote. There's open access versions of it. If you ever want to read any of my papers, just get in touch. It's yeah. Anyway, so I answered the question about wormholes. I answered the antimatter one. I answered the JWST one. We are at the 56-minute mark. I do want to end about 1 hour in. We're going to go over 1 hour, but approximately. So I'm just going to go through and do a quick fire round of all the questions I didn't answer, because I know there were at least 2 or 3 questions that I still have in mind. One about dark matter, one about dark energy. Okay, so taking it from the top. We talked about, I've answered this one about wormholes. I've answered the one about JWST. I've answered matter-antimatter. Okay, then we talked about dark matter bending light. We talked about the known unknowns and philosophy. We talked about Dizzy. I'm just going through doing a quick recap of everything we've discussed today. We talked about Halloween, which was always very fun. This is a good chance, if you ask a question and I didn't answer it, throw it in the comments just in case, and then I'll be sure to see it. Okay, we answered those. We talked about karaoke and all of that cool stuff. Okay, I think it was here a question from Ben that came in 27 minutes or like half an hour ago by now. Are there any other explanations for the accelerated expansion of the universe other than dark energy? Yes, there are. There are ideas that maybe we've just misunderstood the whole concept of gravity, and you can have something called modified gravity, where you take Einstein's general relativity and you modify it in specific ways. This could explain the effects of dark energy, or the effects that we attribute to dark energy. There's also things known as like quintessence, which is a type of field that behaves like dark energy, but is slightly different to dark energy. There's a lot of different ideas. But currently, dark energy is the one that we have found that fits the description best. Sorry, quintessence is a type of dark energy. So there's a lot of different ideas behind what dark energy could be. But for now, we don't know enough to say much other than it's driving the accelerated expansion of the universe. We don't really know what it is. But there are alternatives like modified gravity that tries to explain the results in a different way. And there's other ideas. Maybe there's a fifth force. But then at the end of the day, it's a question of if what you're describing behaves exactly the same way as dark energy, why not call it dark energy? So because dark energy is quite a broad idea, there's a lot of different models that fit within that picture. So there are other explanations, but generally dark energy is the one we found so far that best fits all of the data we have. Okay, just after that, there was a comment from Guadav. These were the 2 comments I was checking for. Comment from Guadav: I have a hunch there might be multiple types of dark matter, not just one. It feels unlikely that a single particle accounts for 25% of all missing mass. Just a gut feeling, no data. That is an excellent point, Guadav. I love that question, that comment. So we know that all of the matter that we see, all normal matter, baryonic matter, normal matter, whatever you want to call it, has 17 building blocks. I showed this last week at the end of the stream. We have quarks, we have fermions, we have bosons, all of these come together. There are 17 different particles that we know of in our standard model of particle physics for normal matter. Normal matter is 5% of the energy content of the observable universe. Dark matter is 25%. Do we really think dark matter is going to be one thing? Probably not. Maybe not. It's hard to be sure about if dark matter is going to be one thing or multiple things. There's also ideas that you could have a whole rich dark sector where you could form dark atoms or nuggets of dark matter. Much the same way to how our standard model behaves, you could have a whole dark sector. Now, the problem is, how do you go about finding 10 different types of dark matter? You have to start somewhere, right? So you start by looking for multiple different models, and if you find them, then you can see, is that enough to explain all of the dark matter? A classic example of this is primordial black holes. If primordial black holes exist, it's unclear if they could be all of the dark matter or only a fraction of the dark matter. So if they're only a fraction of the dark matter, you still need something else to account for the remaining fraction. But rather than looking for 20 things at the same time, we do experiments looking for different things. And usually we focus on specific things. But there are absolutely fun questions to be asked of what if we have multiple types of dark matter that then have some interactions between them? How does this affect our picture? What if we have dark matter with mass and light dark matter that doesn't have mass? How do these interact? How do they behave? So you can make your dark sector very rich. You can add a lot of particles, but we need to start somewhere. So we start by simple models, and then we'll make them more and more complex as we get more data. So you said you have a hunch that maybe there's multiple types of dark matter. You're not the only one. A lot of people are asking this question. It's a very cool question, comment. But at the end of the day, we need to find one type of dark matter before we can talk about finding 100. Of course, it might be that if dark matter has multiple components, looking for one alone is not going to be enough, and we do need to look for multiple components. But we always start with the easiest way to go, which is looking for any type of dark matter, and then we'll figure out if that's enough or if we need more dark matter. But that is a great point there, Guadav. And I saw the question, and I had in mind that I wanted to come back to it because it is a very cool question. Okay, we talked about wormholes some more. I'm just getting to the point where we went into all of the wormhole discussion. Then I went on a tangent about sci-fi. Okay, then we were talking about books, and this is where I stopped with the new comments. The Disney movie, The Black Hole from the 70s, was pretty bad, I've heard. Yeah, I've not seen that, but I feel like I probably wouldn't enjoy it. Comment from David Howden. I've just got round to reading a book I decided to read in my teens. So you're allowed a 30+ year long list of books. Yeah. Yeah, I think adding books to the to be read list and reading those books are two very different hobbies. Comment from Cohen. I saw a video from Anton Pitlov discussing a new study about black holes being the source of dark energy. Any thoughts? No, but you're now the second person in this stream to mention it. So I've made a comment of black holes and dark energy. I haven't yet looked into the study or the videos discussing this, but it sounds really cool. And now two of you have pointed it out. So I've made a note of it. I will try to get to it. I will try to look into that because that is a very cool idea that I've currently not heard about. So now two of you have mentioned dark energy coming from black holes. So I've got a note. I'm absolutely going to look into that because that sounds very cool. Thank you to the two people who asked that. I will try to look into that. Okay, catching up with the final comments here. Comment from Paul: Quintessence should win just because it's a cool sounding name. It is, yes. Although I always forget how to spell it. So, dark energy at least is easy to spell. Two comments from Gwenov. New regime of particles is exciting. It is. And self-interacting dark matter is also very exciting, and also an idea that a lot of people have looked at because you can do a lot of cool stuff if you have a rich dark sector with interactions. It's very cool. David Howden, gotta go. Good luck with the meeting tomorrow. Thank you. Thank you. Yes, I'm very slightly scared about this. I'm sure it will go well. It's a thing. I'll panic about it, but it's going to be fine. Comment from Firth, catching up on the last 15 to 20 minutes. My favorite science reality that's actually fiction is mixed baryon lepton chemistry. Yeah, that's one of those things I'm not going to go into now because we have hit the 1 hour mark. But that is one of those things that sounds like it shouldn't be real, and somehow it is. One of those weird science things. Follow up from Perth. Imagine electrons and moons orbiting top, bottom, and up-down quark baryons with the same atom. Yes. Okay, yes. Looks like I missed a question I asked at the top of the stream. I'll have to catch up on that tomorrow. Perth, yes, you can catch up. The short answer is I've written a paper on it. You're not wrong. Primordial black holes could be the source of the matter-antimatter symmetry if they were evaporating, but there's a bunch of caveats. So you can watch the replay for that. But there is a bunch of caveats. You need a lot of things to happen, but it's a very cool question, a very well thought out question. I wrote a paper on the topic. Ping me if you want more details and if you want the PDF of the paper. But it's a cool question. Perth, watch the replay for more details. Short answer is yes, but with a lot of caveats. Okay, an hour and 5 minutes. As I mentioned at the beginning of the stream, I am going to cut it today because I just want to make sure I get to bed early. I want to make sure I'm well rested for tomorrow. I have a bunch of stuff going on tomorrow, and I just can't risk being tired, or worse, I cannot risk having a long COVID flare up tomorrow. So I want to make sure I get some rest in tonight. So going to cap it at 1 hour and 5 minutes today about that. But yeah, this has been great fun. I love some of the questions. As always, I come into these streams, without a plan most of the time. I'll talk for 10 minutes about CMB and dark matter, and then see where you guys take it. And I love that you asked about wormholes and about black holes and about, cool stuff, what's happening currently in science. It's really fun. I love all of the questions. I love all of the comments. Thank you all for sending me positive messages about tomorrow. Thank you. I do appreciate it. It's going to be fine. It's not a big deal. I'm just making it a bigger deal than it is. It's all going to be fine. Yeah, you follow me on Mastodon. Yeah, Preth, I think you follow my personal one. Reach out to me on either. It's fine. If you all want to follow me on Mastodon, I have two accounts: one personal one and one for Science Outreach. The Science Outreach one is dchooper91_cosmo at astrodon.social. And my private one, it's linked to, you can find it if you really want to, if you're persistent enough, you'll find it. But there's the Science Outreach one. You can also just go to cupofcosmology.com and click all the buttons, and you'll link to the Twitch, you'll link to YouTube, you'll link to Mastodon, all the places you can find me. Okay, so this has been super fun, as always. Cup of Cosmology should be online next Sunday, unless I'm building a greenhouse. But Cup of Cosmology should be online next Sunday, same time as always. That is 7 p.m. if you're in Central Europe, 1 p.m. if you're on the East Coast of the US, 10 a.m. if you're on the West Coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. But in principle, Cup of Cosmology should be back online next week, same time as always. I hope to see you all there. And I hope in the meantime, you will take care of each other and stay curious.